Hello, my name is Bernd Singh. I'm a senior lecturer in mathematics. You are probably all familiar with tilings from your bathroom floor or being a busy bee. If you want to have it more fancy, here are some more examples that you might recognize either from Islamic art or, or from Johannes Kepler's works. In the 19th century, mathematicians looked at these patterns with the help of group theory and, for example, determined that they are up to symmetry. When it comes to symmetry, there are only 17 different wallpapers. They also calculated that there are 230 space groups. That's, for example, important in solid state physics to explain what are the properties of metals, alloys, and semiconductors. Of course, mathematicians pushed on, so to higher dimensions, and did some calculation there, but the important thing here to notice here is that in 2 and 3 dimensions that surround us, periodic patterns like your bathroom floor, it's impossible for such a periodic pattern to have 5-fold or rotational symmetry or rotational symmetries of order greater than 6. So 8-fold or 12-fold symmetries are not possible. Let's jump forward a bit in time to the 60s when computers came about and computational questions emerged. So how one was looked at domino problems. For example, how can you fit dominoes together here such that the colors at the edges match? And then questions arise like, if you are given a certain set of dominoes, right, each type infinitely often, can you tile the whole floor, the whole plane with it? And exploring this further, he asked 2 questions, namely, is there a set of tiles that can tile the plane non-periodically, but it's not possible to, with the same set, to tile the plane periodically? And the second question was, is there a general way, so an algorithm, to tell if a given set of tiles can tile the plane at all? He showed that if the answer to the second question is no, then the answer to the first one is yes. Why is this difficult? If you look here at one puzzle tile, it's one puzzle tile that has some ridges and notches. You see that we have to go out 6 layers or 4 layers here until we get stuck. So it's very difficult to answer these questions because, right, you make a puzzle mistake somewhere and you get stuck at a very different place. However, his student answered and gave an example with a lot of tiles, and later on, of course, people simplified that and gave smaller examples. For example, Raphael Robinson had these set of tiles where the lines on the tiles have to then fit on the edges again. And the thing to notice here and how he proved that this is a non-periodic tile is because these lines that are on the tiles form bigger and bigger interlocking squares. Here is Penrose examples where again you have to match the markings on the edges, and if you do that successfully you get this Penrose tile. Okay, that was in the 70s. In the 80s, now things get real in the sense that crystallographers, then Schechtman, discovered alloys that showed 5-fold symmetry, a symmetry that was forbidden, as we mentioned a few minutes ago. And indeed, other people then also around that time found other alloys that also showed this behavior. Then Schechtman, 10 years ago, for example, got the Nobel Prize in Chemistry for this discovery. And the question is maybe here, what has mathematics to say about that? The amazing thing is that around the same time, mathematicians looked at ways to create such patterns just by coincidence, either by projecting 6-dimensional cells into 3 dimensions or 5-dimensional point sets into 2 dimensions. And if you do this, for example, from 5 dimensions to 2 dimensions, you exactly recover here the Penrose tiling on the right. And the diffraction pattern is shown on the left, and it shows this 5-fold symmetry. Both show this 5-fold symmetry in some sense that is forbidden. Here is an example, the Armand-Binker tiling, that shows 8-fold symmetry, again a symmetry that is forbidden. So I work in this intersection of various disciplines, but also various fields of mathematics, on the right, exploring this region between nice periodic order and randomness. And just to show you how far you can push this, let's consider this Armand-Binker tiling, right? It consists of square and rhombs. Here is the diffraction pattern again. It only shows what physicists call Bragg peaks. So that's an indication that there is long-range order in this pattern. If we now concentrate on the vertices of our squares and rhombs and just consider them, and then we stand in the center of this picture, in the center point, and look around us, then some points will be visible to us and others will be invisible because they are behind other points, and therefore we can only see the frontmost point but not the ones that come behind it. So let's remove all the invisible points, and again we are able to calculate here the diffraction spectrum. And that's how it looks like. It's a bit more complicated, but still it only shows Bragg peaks and therefore shows long-range order and no randomness. Okay, I thank you for your attention and I stop here. Thank you.